Alright, in this video I want to talk about the closed interval method, which is simply a way of finding absolute maximums and minimums of continuous functions on a closed interval. And what we do is we simply find the critical numbers that fall within our interval, and then we take those numbers along with the endpoints and we plug them back into the original function. The biggest is the absolute max, the smallest is the absolute min. And before I do a specific example, geometrically this makes, I think, sense if you think about it. Suppose our function does something like that, and then maybe it keeps going. Who knows? Well, if we only look at, maybe sort of one specific interval, where do I want to chop it up at? It doesn't really matter here. Suppose I chop it up. Suppose this is my A, and suppose we make B over here. Okay, so really when we're looking at the closed interval, we're only looking at sort of this section that I have in red, okay? Well, what happens, if you kind of just restrict yourself, to that little chunk of the graph? Well, certainly, if we're trying to find the smallest and the largest values, it certainly makes sense to look at sort of local minimums and local maximums, and to find local minimums and local maximums that's at critical points, either where the derivative is 0 or undefined. Maybe I even take, kind of a longer section. Suppose we stick B over here. So now suppose I'm looking at this whole section. If you wanted to find the absolute maximum, it certainly would occur, at this place where the derivative doesn't exist. But in this case, the minimum would actually occur at an endpoint. And, in terms of the original graph, that's certainly not going to be a critical number. So that's why you have to look at, the critical points, which is where the derivative is 0 or undefined, but you also have to look at the endpoints. So just kind of a little geometric argument as to why we're doing what we're doing. Nothing more complicated than that. So the function that I want to do here is I'm going to find the absolute maximum and the absolute minimum of this function x squared minus 4 over x squared plus 4 on the interval -4 to 4. So the first thing I'm going to do is just find the critical points. So I'm going to take the derivative. And to take the derivative here, we're just going to have to use the good old quotient rule. So it says we take the denominator times the derivative of the numerator. Well, the derivative of x squared is going to be 2x. The derivative of our constant is just 0, so I'm going to leave that off. Minus, then we'll just take the numerator and multiply that by the derivative of the denominator. Again, we're just get 2x plus 0, so I'm just going to simply write 2x. And then we simply take the denominator and we square it. So I'm going to simplify the numerator. This 2x is going to get distributed to both terms. So 2x times x squared is going to be 2x cubed. 2x times positive 4 is going to give us 8x. The 2x is going to get distributed along with the negative. You can think about it as really being negative 2x if you want to think about it as being over there. So negative 2x times x will be negative 2x cubed. And negative 2x times negative 4 will be positive 8x. Then we have our denominator still, x squared plus 4 squared. So one last thing here, it looks like if we simply clean up the numerator, 2x cubed minus 2x cubed, we've got 8x plus 8x, which is 16x. And then we have our denominator, x squared plus 4 squared. Okay, so now I've got to find the critical numbers. And to find the critical numbers, that's just where, again, the derivative equals 0, or where the derivative is undefined. But for the derivative to equal 0, the numerator of the fraction is what has to equal 0. For the derivative to be undefined, the denominator of the fraction would have to equal 0. Well, and then we'll just simply solve both equations for x. So the first one's pretty easy. We can just divide by 16, and that'll give us x equals 0. Well, the second one, if you think about it, I think it's pretty clear there's no solution, because what number can you square and then add 4 and then square it and get 0 at the end? But likewise, if you take a square root of both sides, maybe if you didn't notice that, you get x squared plus 4 equals 0. And again, that makes sense. It says the inside has to be 0. Then if you subtract negative 4 and try to take square roots, well, you can't take square roots of negative numbers without using imaginary. And we're just working with real numbers. So the only critical number we find is x equals 0. Now I have to go back and make sure that that falls in the specified interval, and certainly 0 does fall between -4 and 4, so we will use it. Suppose we found two critical numbers. Suppose we found x equals 0 and x equals 30. Well, in this particular problem, had we found another critical number, if it's outside of this interval, we simply don't use it. And that just simply means, x equals 30, that's just simply a part of the graph we're not concerned with. Okay, so my only critical number here was x equals 0. Our endpoints were at x equals -4 and at x equals +4. So now what I have to do is I simply have to go back and plug all of these numbers back into the very original function. I've got to plug them back into this original function. The biggest is going to be the maximum, the smallest is going to be the minimum. So I'm going to plug it back into f of x equals x squared minus 4. So let's see, if we plug in 0, f of 0 would be 0 squared minus 4 over 0 squared plus 4. Well, it looks like we get -4 over +4, which is going to give us -1. If we plug in f of -4, okay, we'll get -4 squared plus 4. Whoops, I was looking in the wrong place. Let's try that one more time. F of -4, we'll get -4 squared, but then in the numerator, hey, we've got -4. And then in the denominator, that's where we get our -4 squared plus 4. So -4 squared is going to be positive 16 minus 4. 16 minus 4 is going to give us 12 in the numerator. -4 squared, that's 16 plus 4, that's going to give us 20. Okay, so what's that? I guess if we divide by 2, I guess we can divide by better than 2, we can divide by 4. If we divide the top by 4, we'll get 3. If we divide the bottom by 4, we'll get 5. Notice if you plug in +4, well, since you're squaring them, you're going to end up getting the same thing. You're going to get 16 minus 4 on top and 16 plus 4 on the bottom. We'll get the exact same value, which is 3/5. Okay, now it simply says all we have to do to pick out the absolute minimum is we just pick out the smallest value that occurs. So in this case, we would say there's an absolute minimum of -1, that's the smallest value, and we would say there's an absolute maximum of, well, 3/5. It's okay that it occurs in two different places. In this case, it occurs at both the endpoints. Nothing wrong with that at all. But again, there's only one maximum value. It's 3/5. Again, it just occurs in different places. Obviously, if you had 2/5 instead, well, -1 would still be the absolute minimum, and 3/5 would still be the absolute maximum. 2/5 would just be, you could probably go back, well, actually it's an endpoint, so not much is going on there. So, again, all you have to do is pick out the largest and the smallest. Again, in this case, the maximum occurred at 2 places, but that's perfectly legal, no problem there. So, nothing too crazy. Again, it can be a little tedious, especially when the derivative gets worse and you're finding all these critical points. But again, you're just taking the critical points that fall in the interval along with the endpoints of the interval. You're plugging those back into the original function to get the maximum and the minimum.